We are Hirotetsu Hongo, Sat Hashimoto, Masaki Natori, and Katsuki Sugiyama. We are in Mea Senior High School SSH Chemistry Club. Today, we are going to make a presentation of our research on the dye-sensitized solar cell, DSC, using anthocyanin. In this research, we have paid attention to anthocyanin, which is a kind of plant pigment and has various colorations. We examined its nature and we did some experiments on using it for DSC. At that time, we attempted to solidify anthocyanin to treat it quantitatively and succeeded in getting solid anthocyanin from 6 kinds of plants. In the next step, we made an attempt to improve the performance of DSC. Please look at this picture. They are plant-pickled eggplants. From the left, eggplants are treated, one with ironate and one with potassium ion. As you can see, the color can be preserved in 4 days about the 2 intervals. That is well known from a long time ago, and it is because anthocyanin in the eggplant skin forms stable case complexes with metal ions into rusty ironate or potassium ion. After this experiment, we got interested in the coloration of anthocyanin and began to research on it. When we researched, it is too expensive for us to buy anthocyanin on the market, so we attempted to extract anthocyanin from familiar plants. The objective is investigation into the nature of anthocyanin and making a more efficient DSC using anthocyanin. Concretely, we did 2 things. The first is solidification of anthocyanin to treat it quantitatively, and secondly, comparing the performance of DSC by changing these 3 conditions.
I will explain basic knowledge about anthocyanin. Anthocyanin is pigment contained in various plants, such as yellow plant skin or red cabbage. Anthocyanin has a chromophore called anthocyanidin. This is basic structure of anthocyanidin. Anthocyanidin is determined by numbers and kinds of functional groups combining with urine. These are the examples of anthocyanidin. Blue rings are hydroxy groups and yellow ring is a methoxy group. This is the structural formula of nacin. This is a delphinidine, 101 cyanidin. Saccharide and organic acid are combined with delphinidine and nacin is made up. Next, I will explain why color of anthocyanin changes and fades according to pH. They are performed. Palladium ion, anhydrous anion, and pseudobase. They are in equilibrium relationship, and equilibrium is inclined according to pH. Under the condition that pH is low, palladium ion increases and the solution becomes red. Under the condition that pH is high, anhydrous anions increase and the solution becomes blue. When you just leave it, pseudobase increase little by little and the solution becomes colorless. This is discoloration of anthocyanin. In addition, it is caused by hydration of anthocyanin.
We conducted the experiment on the solidification as below. First, we put plant pieces into the color made of PET bottle. Then, we poured mineral water solution which contained 5% formic acid into the color to extract anthocyanin. Formic acid maintained the acidity of anthocyanin. After that, we concentrated the extracted solution by rotary evaporator. Next, we passed it through an amber-white X87 HP resin column and absorbed anthocyanin in the resin. Then, we washed it with 5% formic acid water solution and eluted anthocyanin attached to the resin with 5% formic acid mineral solution. At last, we concentrated the eluted solution by rotary evaporator and dried it in a desiccator. In this way, we got solid anthocyanin. First, look at these pictures of solid. They are eggplant, azalea, hydrangea, morning glory, red cabbage, and red radish. Next, look at this picture. This is a picture of anthocyanin which has not been purified. This anthocyanin was viscous. We think that it is necessary to purify the extracted solution for solidification. After solidification, we examine the purity of the solid. We use Lambert wave law. The purity of the solid of nacin was about 16%.
By adding metal ions, anthocyanin changes its state of coloration and discoloration. Anthocyanin forms the chelate complex on the hydroxy group or methoxy groups of purine. We added two metal ions, the aluminum ions and divalent ions, into nasine solution. I will introduce the example, the aluminum ion. In pictures, left sides are acidity and right sides are basic. These figures show the piled absorption spectrum of each pH, and the right figures are 4 days later. We measured them using the absorption method. These are the figures of nasine solution, nothing added. And the others are ones, aluminum chloride added. In comparing them, we saw the aluminum ion stabilized the coloration of nasine.
I will explain about the principle of coagulation of DSC. First, the pigment azote with titanium oxide is photoexcited. Next, the pigment transfers electrons to titanium oxide and becomes oxidation state. Next, the pigment is reduced because it receives electrons from iodide ions. Iodide ions change to triiodide ions. Triiodide ions receive the electrons as a cathode and becomes iodide ions again. This reaction occurs over and over again, and DSC generates electricity. I will tell you how to make DSC. First, mix titanium oxide and nitric acid to make titanium oxide paste. Second, dissolve it on conductive glass. Next, when the paste is dry, bake it at 450 degrees Celsius for 30 minutes with an electric furnace. Then, soak it with anthocyanin solution for 1 day. Next, soak it with ethanol to remove the physically absorbed anthocyanin. Then, use it as anode and use a conductive glass doped with graphite as cathode and pour iodine electrolyte to make DSC. Finally, expose light to it with a projector, measuring an electric current and voltage with a tester for 10 minutes at 1 minute intervals. This shows the emission spectrum of the projector. Mostly they are visible light. Anthocyanin absorbance is 480 nanometer to 580 nanometer wavelengths. Black line is titanium oxide absorbance, and red line is the emission spectrum of solar radiation. By absorbing anthocyanin to titanium oxide, it is possible to use more solar radiation. Next, I will experiment to find a better condition to make DSC. First, I change the particle size of titanium oxide. If particle size of titanium oxide is small, surface area of titanium oxide film and the amount of absorbed anthocyanin increase. So, the performance to generate electricity is improved. Then, I change the particle size of titanium oxide and film thickness on these conditions. In this experiment, I use nothing as an anthocyanin solution. This is the result. These are not absorbed with nothing, and this graph shows voltage value and current value on each condition. As you can see, the smaller the particle size of titanium oxide is, the darker the color is. So I thought the amount of absorbed anthocyanin increased. But 21 nanometer and 40 nanometer titanium oxide showed low current value. I wonder why it does so. Then, I observed the surface of titanium oxide film in detail. 0.2 micrometer titanium oxide was doped as a whole, but 21 nanometer and 40 nanometer titanium oxide gathered at the part and cracks appeared. I think this is the reason why they show low current value. As a result, the condition is appropriate when the particle size of titanium oxide is 0.2 micrometer and film thickness is 160 micrometers. Next, I add signal to titanium oxide paste. If I add signal to titanium oxide paste, it forms porous film. So, surface area of titanium oxide film and the amount of absorbed anthocyanin increase. Then, I add these three kinds of signals. This is the result. From this graph, it shows that the larger molecular weight of signal is, the larger surface area of titanium oxide film is. Polyvinyl alcohol wasn't vaporized at the state of baking, and electrons were difficult to transfer. As a result, the condition is appropriate when signal is polyethylene glycol 6 size. Next, I change the anthocyanin solution conditions. I used 4 kinds of refined or unrefined anthocyanin. I regard the concentration of each unstaining solution as equal by equalizing the ratio of molar absorptivity with the ratio of absorbance of maximal absorption wavelengths. These are unstaining of eggplant, wet cabbage, wet radish. The uncyanidin is delphinidin, cyanidin, tetralphenidin. Delphinidin has 3 hydroxy group on purine, cyanidin has 2, tetralphenidin has 1. So the electron withdrawing type is as follows. This is the result. If the current value depends on only electron withdrawing of hydroxy group in uncyanidin, the current value should be as follows. But actually, the current value is as follows. Wet cabbage and eggplant were as expected, but wet radish was not. So I think this factor is not enough. Then, as another factor, I think uncyanidin is interacted with titanium oxide by forming titanium plate complex. In order to form titanium plate complex, uncyanidin needs more than 2 hydroxyl or methoxy group on purine. But wet radish uncyanidin has only 1 hydroxyl group on purine. So it is difficult to form titanium plate complex. I think this is the reason why it shows low current value. The conclusion is as follows. Current value depends on electron withdrawing and forming titanium plate complex. The appropriate uncyanidin for applying to DSA is cyanidin or meionidin. Difference between refined and unrefined uncyanidin doesn't show consistent tendency in current value. The perspective is as follows. The bibliography is as follows. And as acknowledgement, I'd like to thank Professor Yoshida Kumi, PhD, Laboratory of Natural Products and Bioorganic Chemistry Graduate School of Information Science, Nagoya University. That's all for our presentation. Thank you for your listening.
ありがとうございました。植物から抽出されるアントシアニンの性質と色素増感太陽電池への応用、愛知県立明和高等学校の皆さんでした。ではこれより質疑応答とさせていただこうと思います。ご質問のございます方、挙手でお願いいたします。はい、あちらに手を挙げていらっしゃる水色の洋服を着た方にマイクをお願いいたします。
講演ありがとうございました。実験1番アントシアニンの固体化のところで今後の展望としてさらなる生成のジェルの工夫をしようとしていらっしゃるということだと思うんですけれども、具体的にどんな工夫をしようというその計画ならありましたら教えていただきたいんですけれども。
ご質問ありがとうございました。そうですね、高校でできる範囲でですと、他の種類のアンバーライトというこちらの樹脂を使えば、もう少し純度を上げることはできるのではないかと考えているので、今後、違う種類のアンバーライトを使っていきたいと思っております。
はい、ありがとうございます。
ありがとうございました。もう一方、よければご質問ございましたら、はい、すいません、前の方、男性の方によろしくお願いいたします。
ありがとうございます。アントシアン系の色素に関してのその色素と乾電池は結構高校生が緩和せる文献でも発生効率かなり悪いというふうに書いてたりします。その中でも解放電圧とか単圧電流とかそこまで調べてなさってまして、一番の君たちの売りというものは何だったのかっていうのを改めてお伺いしたいです。
ご質問ありがとうございます。僕たちはもともとはアントシアニンについて最初調べていて、そこから発展していろんなものに応用できないかということを考えていて、そこで色素増感太陽電池というものがあるということを知って、色素増感太陽電池にまず利用できないかと考えて考えました。でも一般的に使われる色素増感太陽電池の色素っていうのは僕たち高校生にとってはとても高価なもの、リプゲニウム作体とかとても高価なものなんで、でもアントシアニンっていうのは植物から取れるんで、コスト的にはそんなに高くないということで、それを使って高校生でもできるような身近な色素増感太陽電池を作って、それを使うことができないかということを考えて、コスト面が やはり高校生でもできるものなので、このアントシアニンというものを色素増感太陽電池に応用しようと思いました。
ありがとうございます。
ありがとうございました。
ありがとうございました。お時間の方が参りました。以上、オーラルプレゼンテーションに植物から抽出されるアントシアニンの性質と